Imagine standing in New York Harbor on a quiet morning. Ferries move across the water. Tourists raise their phones. Ahead of them, the Statue of Liberty stands exactly where she has stood for generations, green against the sky, torch lifted above the Atlantic like a promise that this city will always endure. Now imagine the ocean beginning to rise, not in a storm, not in a hurricane, not in a single violent wave. It simply keeps climbing. At first, the water slips over the docks of Liberty Island. Then it covers the lower steps. Then the base of the pedestal disappears. The sea keeps rising, swallowing stone, steel, and concrete with terrifying calm. Soon the water reaches Lady Liberty's feet, then her robe, then her chest. Eventually, only her torch remains above the surface, a lonely shape over an endless sheet of dark water. And then that disappears too. Across the harbor, Manhattan follows. The financial district goes first. Wall Street sinks beneath the Atlantic. Subway tunnels fill. Glass towers stand for a moment like isolated monuments above a new inland sea, until even they begin to look like the ruins of a civilization no one can save. And New York is only the beginning. Farther south, Miami vanishes. Most of Florida is so low that in a world of rising seas, the state does not fight the water for long. It simply yields. New Orleans goes under. Houston floods. Washington, D.C. becomes a shallow bay. On the other side of the continent, San Francisco Bay spreads far inland, and California's map starts to look wrong. Wrong because everything familiar is gone. This sounds like science fiction, a disaster movie, an impossible future designed to shock an audience. But the number behind it is real. If all the ice on Earth melted, sea levels would rise by roughly 65 meters, more than 200 feet. That is enough to redraw the map of human civilization. Every major coastal city changes. Entire shorelines retreat inland. Ports disappear. Airports vanish. Beaches become memory. Properties worth trillions become worthless. And the places humans chose for trade, power, and empire suddenly become the most dangerous places on Earth. But the strangest part is not the number. The strangest part is that Earth has already lived in a world without great ice sheets. Long before human history, before kingdoms and writing and war fleets, this planet knew oceans higher than ours and poles far warmer than anything we have ever seen. There were times when the frozen Earth we take for granted did not exist at all, which means the world we call normal may not be normal. It may be temporary. And that raises a bigger question. If ice can vanish, why was it here in the first place? Why does this planet sometimes become a greenhouse world and sometimes lock itself in ice? Because the truth behind this story is far stranger. 65 meters. It is just a number, 2 digits written on a page. But on a planetary scale, that number changes everything. Raise the ocean by 65 meters and the familiar outline of the continents begins to dissolve. Coastlines retreat deep into the interior of continents. Bays widen into seas. Rivers stretch far inland as saltwater pushes upstream through valleys carved thousands of years ago. The world map that humanity has memorized for generations suddenly becomes useless. The eastern coast of the United States collapses inward. Florida disappears almost entirely beneath the Atlantic. New Orleans sinks below the Gulf of Mexico. Even the capital of the country sits dangerously close to the rising edge of the sea. Across the Atlantic, Europe changes just as dramatically. The Netherlands, a nation that has spent centuries fighting the ocean, vanishes almost completely. Denmark fragments into scattered islands. Northern Germany becomes a wide, shallow gulf reaching toward the center of the continent. Asia loses some of its most crowded landscapes. Bangladesh, one of the most densely populated places on Earth, loses most of its land. The great cities built at the mouths of rivers, Shanghai, Bangkok, Mumbai, struggle against a sea that no wall can truly hold back. And all of this happens because of ice. Or more precisely, because of the unimaginable quantity of frozen water sitting quietly at the poles of our planet. Right now, Earth stores roughly 26.5 million cubic kilometers of ice. Most of it rests in Antarctica, a continent so cold and isolated that its ice sheet in some places reaches nearly 5 kilometers thick. Greenland holds another enormous reserve. Beyond them lie thousands of glaciers scattered across mountain ranges from Alaska to the Himalayas. Together, they form the largest store of fresh water on the planet. If it melted, every drop would eventually reach the ocean, and the oceans would rise. But here is where the story becomes more complicated and far more interesting. Because the frozen Earth we see today is not the version of the planet that existed for most of its history. For enormous stretches of geological time, ice sheets like Antarctica simply did not exist. The poles were warm. Forests reached far north and far south. Creatures that today live only in tropical climates once roamed lands that are now buried beneath kilometers of ice. In other words, our planet has switched between two very different states: a greenhouse world, warm and largely free of ice, and an icehouse world, where glaciers dominate the poles and shape the climate of the entire planet. Right now, humanity happens to live inside one of those rare icehouse periods. The great ice sheets that hold back 65 meters of ocean are part of that temporary chapter in Earth's history. Which raises a deeper question. Why does the planet ever enter an age of ice at all? What forces are powerful enough to freeze entire continents? And how did those frozen worlds shape the environment where human civilization eventually appeared? To understand that mystery, we have to step far outside the timeline of human history and look at the planet on a much larger scale. Because once we do, something surprising appears. For most of Earth's past, there was no ice anywhere on the planet. To understand what would happen if all the ice on Earth melted, we have to step outside the modern world. We have to forget the map we know. Forget Greenland buried beneath kilometers of ice. Forget Antarctica locked in a silent white desert. Forget glaciers clinging to mountain ranges from Alaska to the Himalayas. And forget the drifting sea ice that covers much of the Arctic Ocean each winter. All of it feels permanent to us. It feels ancient, as if Earth has always looked like this. But the truth is far stranger. For most of the planet's history, the Earth had little or no permanent ice at all. If we could travel back tens of millions of years, long before humans existed, we would find a world that feels almost impossible compared to today. The poles were not frozen wastelands. They were alive. Forests grew where ice sheets now stand. Rivers flowed across landscapes that today lie buried beneath kilometers of frozen water. The air was warmer. The oceans carried heat farther toward the poles, and the difference between tropical climates and polar regions was far smaller than it is today. Scientists call these long intervals greenhouse worlds. During greenhouse periods, global temperatures were higher and permanent ice barely existed anywhere on the planet. Instead of massive frozen caps locking away huge amounts of water, the oceans were slightly higher and coastlines stretched farther inland. The planet was still Earth, but it operated under a completely different climate system. And the evidence for this lost world is not speculation. It is written directly into the rocks. In the far north of Canada and Alaska, paleontologists have discovered fossils that should not exist in the Arctic. Remains of crocodile-like reptiles, giant turtles, thick forests that once grew in soils that today remain frozen year-round. These were not rare animals barely surviving in the cold. They were thriving. The Arctic, which today spends much of the year in darkness and ice, once supported entire ecosystems filled with warm-adapted plants and animals. Rivers carried sediment through wetlands. Dense vegetation covered the land. Life spread across regions that now seem permanently hostile to it. And Antarctica tells an even more surprising story. Today, it is the coldest continent on Earth. Temperatures plunge far below freezing. Ice stretches across the land in a frozen plateau more than 3 kilometers thick. Powerful winds sweep across a barren white landscape where almost nothing lives. But beneath that ice, scientists have discovered something remarkable: fossilized forests. Leaves, pollen, and ancient wood preserved in Antarctic sediments reveal that the continent was once covered with vegetation. Rivers once flowed across valleys that are now buried beneath glaciers. Entire ecosystems flourished where, today, only ice and wind remain. If you had stood in Antarctica during those distant ages, the landscape would have looked nothing like the one we know. Instead of a frozen horizon, you might have seen forests, rivers, and a climate closer to southern Chile or New Zealand than the brutal Antarctic cold of today. And the Arctic may have been even warmer. Some geological evidence suggests that during certain ancient warm periods, the Arctic Ocean reached temperatures close to 20 degrees Celsius. Waters that are now choked with drifting ice may once have been mild enough to support ecosystems that seem almost tropical compared with today. In those ancient worlds, the poles were not engines of cooling. They were simply part of a warm planet. And that difference matters far more than it first appears, because ice is not just scenery at the edges of the world. Ice reflects sunlight back into space. It cools the atmosphere. It influences ocean currents, weather patterns, and the stability of the seasons that modern ecosystems depend on. The great ice sheets act like part of the planet's climate machinery. Remove them, and the balance of the entire Earth system begins to change. But in those earlier ages, that machinery had not yet formed. The Earth operated under a different equilibrium, a warmer one, where oceans held more heat and polar regions remained free of permanent ice. For millions of years, that warm balance held. And then, slowly, something began to change. Temperatures began to fall. Forests retreated from the highest latitudes. Snow that once melted every summer began to linger a little longer. What had once been temporary started to become permanent. Ice began to appear. At first, only small glaciers in the coldest regions. Then, larger ice sheets began to form. Eventually, entire continents started to freeze. The modern ice-covered Earth was beginning to emerge. But this transformation did not happen simply because the planet cooled. Something deeper was happening. Something involving the movement of continents, the flow of ocean currents, and the geography of the entire planet. And once that shift began, it allowed the first great ice sheets to grow. But the real surprise came later, when scientists finally measured how much ice the planet holds today. Because the amount of frozen water sitting quietly at the poles is far greater than most people ever imagine. For millions of years, the warm Earth remained stable. Forests reached high latitudes. Oceans carried heat freely between the poles and the tropics. Sea levels were higher, and coastlines extended far inland across the continents. The planet had found a balance. But that balance depended on something surprisingly fragile: the way continents were arranged across the surface of the Earth. Because continents do not stay still, they drift slowly across the planet, moving only a few centimeters each year. Yet over tens of millions of years, those tiny movements reshape the entire geography of the world. Oceans open, land bridges collapse, mountain ranges rise, and the circulation of heat across the planet begins to change. One of the most important of these changes happened far to the south. Roughly 34 million years ago, Antarctica was not the isolated continent we see today. It was still connected, in places, to other land masses. Warm ocean currents could reach its shores more easily, carrying heat from lower latitudes. But as the continents continued their slow drift, something dramatic occurred. Antarctica separated completely from South America. A new ocean passage opened between them, a deep stretch of water that would eventually become known as the Drake Passage. At first, this might have seemed like a minor change on a global scale, but in the long history of Earth's climate, it would become one of the most important events ever recorded. Because once that passage opened, the oceans were finally able to circulate freely around Antarctica. And when that happened, a powerful current began to form. Today, scientists call it the Antarctic Circumpolar Current. It is the largest ocean current on Earth. Unlike other currents that bend and curve through ocean basins, this one circles the entire continent without interruption. Driven by powerful winds and the rotation of the planet, it moves vast volumes of water endlessly around Antarctica. And that current does something remarkable. It isolates the continent. Warm water from the tropics can no longer easily reach Antarctic shores. The current acts like a barrier, trapping cold water around the continent and preventing heat from circulating southward. Slowly, Antarctica began to cool. Snow that once melted during the warmer months began to survive through summer. Year after year, that snow accumulated. Layer after layer compressed under its own weight, gradually transforming into ice. At first, the glaciers were small, but once permanent ice began forming on the continent, a powerful feedback loop started to take hold. Ice reflects sunlight far more efficiently than rock or soil. As more ice formed, more sunlight was reflected back into space, allowing temperatures to fall even further. The colder it became, the more ice could grow. And the more ice grew, the colder Antarctica became. Over millions of years, the process accelerated. Glaciers expanded across valleys. Ice sheets spread outward from the highlands. Eventually, the continent was buried beneath an enormous frozen cap, one that would grow to hold the majority of the planet's ice. Antarctica had become a frozen continent, and once that happened, the climate of the entire planet began to change. The presence of a massive ice sheet at the South Pole altered global ocean circulation. It influenced atmospheric patterns, seasonal cycles, and the way heat moved between the equator and the poles. The Earth was slowly shifting from a greenhouse world into something colder. But Antarctica was only the beginning. Because once large ice sheets existed in one part of the world, the planet became far more capable of entering full ice ages. Over time, additional glaciers began forming in mountain ranges across the northern hemisphere. Eventually, enormous ice sheets would grow across North America and Eurasia. But long before those dramatic ice ages arrived, scientists made a discovery that revealed something astonishing. They realized that the frozen reservoirs of Antarctica and Greenland were storing an almost unimaginable amount of water. Water that, if released back into the oceans, could change the shape of every coastline on Earth. And that realization would lead scientists to ask a simple but unsettling question. Exactly how much ice is our planet holding today? For most of human history, the great ice sheets at the ends of the Earth seemed distant and silent. They were there, but they felt irrelevant to the rest of the planet. Early explorers who reached Antarctica described a place that felt almost otherworldly. Endless white horizons, winds powerful enough to tear apart tents and equipment, temperatures so cold that exposed metal could become brittle as glass. To those who first stepped onto the continent, Antarctica looked empty, a frozen desert stretching beyond the limits of human survival. Greenland appeared similar, a vast plateau of ice rising above rugged coastlines, cut by glaciers that slowly flowed toward the sea. To explorers and sailors, these places were obstacles, but to scientists, they would become something far more important. Because hidden inside those enormous ice sheets was one of the most extraordinary archives on Earth, a record of the planet's past, written layer by layer into the frozen surface. The discovery of that archive began with a simple observation. Snow does not always disappear. In most places on Earth, snow falls during winter and melts again in spring. But in the coldest regions of Antarctica and Greenland, the temperature rarely rises above freezing. Snow that falls during one season may remain through the next. Year after year, new snowfall covers the older layers. Over time, the weight of those layers compresses the snow beneath them. The crystals tighten together, slowly transforming into denser ice. What began as light snowfall becomes a solid, frozen layer buried beneath the surface. And that process repeats again and again. Each year leaves behind another thin page in a growing frozen record. Over centuries, those pages accumulate. Over thousands of years, they sink deeper into the ice sheet. And over hundreds of thousands of years, they create enormous stacks of climate history, preserved in ice. Scientists eventually realized that if they could drill deep enough into those ice sheets, they could recover that record layer by layer, almost like reading the pages of an ancient book. But there was something even more remarkable hidden inside the ice. Air. As snow compresses into ice, tiny pockets of air become trapped between the crystals. These bubbles are microscopic, but they contain something extraordinary. Samples of the atmosphere from the exact moment the snow originally fell. In other words, the ice preserves pieces of ancient sky. For the first time in history, scientists had a way to measure the atmosphere of the distant past directly, not through models or guesses, but through real samples preserved for hundreds of thousands of years. To reach those samples, drilling teams began working in some of the most remote locations on Earth. Deep in Antarctica and Greenland, scientists built temporary research camps on top of the ice sheets. Specialized drilling equipment was lowered slowly into narrow holes cut into the ice. The drills extracted long cylindrical sections, ice cores, which were carefully lifted to the surface and stored for analysis. Each cylinder represented thousands of years of snowfall compressed into frozen layers. And the deeper the drilling went, the farther back in time those layers reached. Some ice cores eventually revealed climate records stretching back more than 800,000 years. Inside those cores, researchers began measuring the chemistry of each layer. They analyzed oxygen isotopes that revealed ancient temperatures. They identified traces of volcanic ash carried across continents by the wind. They studied dust particles blown from distant deserts during colder periods. But the most important discovery came from the trapped air bubbles. By measuring the gases inside them, scientists could see how concentrations of carbon dioxide and methane had changed through time. What they discovered was astonishing. The climate of Earth was not stable. It moved through enormous cycles. Temperatures rose and fell over tens of thousands of years. Ice sheets expanded across continents during cold periods and then retreated again when the planet warmed. The deeper the cores were studied, the clearer the pattern became. The Earth was constantly shifting between colder and warmer states. Long glacial periods, when ice sheets spread across large parts of the northern hemisphere, were followed by warmer intervals when the ice retreated and sea levels rose again. These changes were happening long before humans existed, long before cities, long before agriculture. The planet had always been moving through these enormous climatic rhythms. But as scientists continued analyzing the ice cores, another realization slowly emerged. The ice sheets themselves were not just recording the climate. They were controlling it. When the planet cooled, snow accumulated and ice sheets grew larger. The bright surfaces reflected more sunlight back into space, allowing temperatures to drop further. The cooling strengthened itself. But when the planet warmed, the opposite happened. Ice melted. The reflective white surfaces shrank. Darker land and ocean absorbed more sunlight. Warming intensified. And with that warming came something else. Rising seas. Water that had once been locked away inside ice sheets slowly returned to the oceans. Coastlines moved inland. Entire landscapes that once stood above the sea disappeared beneath it. This realization changed how scientists looked at the frozen poles. Antarctica and Greenland were not simply frozen landscapes. They were enormous reservoirs. Gigantic stores of fresh water holding back vast amounts of ocean. And that led to a question that would redefine how researchers thought about the stability of the modern world. Exactly how much water was locked inside Earth's ice? Because if even a portion of it melted, the consequences would not remain confined to the poles. They would reach every coastline on Earth. And once scientists began calculating the total amount of ice stored across Antarctica, Greenland, and the world's glaciers, the number they discovered was far larger than anyone had expected. A number capable of redrawing the map of civilization. Once scientists understood that ice cores contained a record of ancient climates, the next step seemed obvious. They needed to measure the ice itself. How much was there? How thick were the ice sheets? And most importantly, how much water did they contain? At first glance, the frozen continents looked simple enough. Antarctica appeared as a vast white plateau. Greenland looked like a massive cap of ice covering an island. But the deeper researchers studied them, the more complicated the picture became. Because ice sheets are not flat. They are landscapes. In Antarctica, the ice rises into domes and ridges, flows slowly through valleys, and collapses into enormous glaciers that slide toward the ocean. In some places, the frozen layer is relatively thin. In others, it becomes almost unimaginable in scale. In the deepest parts of the Antarctic interior, the ice reaches nearly 5 kilometers thick. That is taller than many mountain ranges. Standing on the surface there, a person is not standing on land at all. Beneath their feet lies a mountain of frozen water, thousands of meters deep, resting on rock that may be far below sea level. Greenland tells a similar story. At the center of the island, the ice forms a massive dome that slowly spreads outward in all directions. Gravity pulls the ice toward the coast, feeding enormous glaciers that eventually break into the ocean as towering icebergs. From space, the movement is almost invisible. But over years and centuries, the ice is constantly flowing. Scientists began measuring these enormous frozen structures using aircraft radar, satellite data, and ground surveys. By mapping the thickness of the ice across entire continents, they were finally able to estimate the total volume stored at the poles. The numbers were staggering. Antarctica alone holds the vast majority of the planet's ice, roughly 26.5 million cubic kilometers of frozen water. The continent contains nearly 90% of all the ice on Earth. Greenland adds another massive reserve. And beyond those two giants, thousands of glaciers stretch across mountain ranges around the world, in Alaska, the Andes, the Alps, the Himalayas, and countless other high landscapes where snow accumulates year after year. Together, these frozen systems form the largest storage of fresh water on the planet. But the discovery that shocked scientists was not just the total volume. It was what that volume represented. If all that ice melted, every drop would eventually find its way into the ocean, and the oceans would rise. Not by a few centimeters, not by a few meters, but by an amount large enough to transform the geography of the entire planet. When researchers converted the volume of ice into sea level equivalents, the result was astonishing. If the Antarctic ice sheet melted completely, global sea levels would rise by roughly 58 meters. Greenland alone would add another 7 meters. Glaciers around the world would contribute a little more. Add them together, and the total approaches 65 meters of potential sea level rise. 200 feet. Enough water to erase much of the world's modern coastline. This realization forced scientists to look at the frozen poles in a completely new way. They were no longer just remote environments studied by polar researchers. They were critical components of the entire Earth system. Gigantic reservoirs controlling the position of the world's oceans. Every coastal city on the planet existed because that water was currently locked away as ice. New York, London, Shanghai, Mumbai, Tokyo, Sydney, all of them sit at the edge of seas that remain lower only because Antarctica and Greenland are holding trillions of tons of water in frozen form. If that balance changed, the consequences would not remain confined to the polar regions. They would reach every harbor, every delta, every island nation, and every coastal plain where humans have built their civilizations. And that is when the scale of the problem became clear. Because scientists had not only discovered how much ice existed on Earth, they had also discovered something else. Ice does not melt all at once. Different parts of the planet respond to warming at different speeds. Some glaciers retreat quickly, others remain stable for centuries. Certain ice sheets may collapse suddenly while others change far more slowly. In other words, the disappearance of Earth's ice would not be a single event. It would unfold in stages, and each stage would reshape the planet in ways that are difficult to imagine. To understand what those stages might look like, scientists began asking a new question. If the ice started melting, which parts would disappear first? And the answer to that question would reveal something even more surprising. Because not all ice on Earth has the same power to change the oceans. Once scientists understood how much ice the planet was storing, a new challenge emerged. They needed to understand where that ice actually was. Because the frozen water of Earth is not evenly distributed across the planet. It exists in several different forms, scattered across different regions, each behaving in its own way. Some ice floats on the ocean, some sits on top of land, and some of it rests on land that lies below sea level, hidden beneath enormous frozen sheets. Each of these types of ice affects the oceans differently. To understand the future of sea levels, scientists had to examine them one by one. The first category is the one most people recognize immediately: glaciers. Glaciers exist across mountain ranges all over the world. In Alaska, rivers of ice flow slowly through deep valleys toward the sea. In the Andes, glaciers cling to steep slopes above high plateaus. In the Alps, remnants of ancient ice still remain in shaded basins between peaks. Across the Himalayas, thousands of glaciers stretch through some of the highest landscapes on Earth. From a distance, they appear almost motionless, but glaciers are constantly moving. Snow accumulates in their upper regions, compressing into ice under immense pressure. That ice then begins a slow downhill journey, flowing under its own weight toward lower elevations. Eventually, the ice melts, breaks apart, or collapses into rivers and lakes below. For centuries, these glaciers have acted like frozen reservoirs, storing water that slowly feeds many of the world's major rivers. But glaciers also respond quickly to rising temperatures. When the climate warms, they shrink, and across the planet, that shrinking has already begun. Satellite imagery, aerial surveys, and ground measurements all tell the same story. From the Rocky Mountains to the European Alps, from Patagonia to the Himalayas, glaciers are retreating. Ice that accumulated over centuries is slowly melting away. Yet despite how dramatic these changes can appear, glaciers are actually responsible for only a small portion of the planet's total ice. All of the mountain glaciers on Earth combined contain roughly 170,000 cubic kilometers of ice. That may sound enormous, and in human terms, it certainly is. But compared to the ice sheets at the poles, it is relatively small. If every glacier outside Greenland and Antarctica melted completely, global sea levels would rise by less than half a meter. Enough to cause serious flooding in some coastal regions, but nowhere near the 65 meters scientists calculated earlier. The true giants of Earth's ice system lie elsewhere. The next major reservoir sits far to the north, Greenland. Seen from space, Greenland looks like a vast white dome surrounded by dark ocean. Almost the entire island is buried beneath an ice sheet that has been accumulating for hundreds of thousands of years. At its center, the ice rises more than 3 kilometers above the bedrock below. This ice sheet behaves very differently from mountain glaciers. Instead of forming narrow rivers of ice between mountains, the Greenland ice sheet spreads outward from a central dome, flowing slowly toward the coast in every direction. Along its edges, enormous glaciers push toward the sea, where they fracture and release massive icebergs into the North Atlantic. These glaciers move constantly, though their motion is slow enough to escape human perception. Over decades and centuries, however, the movement becomes clear. Ice flows outward, and when the climate warms, the flow accelerates. Greenland alone holds enough ice to raise global sea levels by more than 7 meters if it melted completely. That is enough to flood large sections of many modern cities. Yet even Greenland is not the main source of Earth's frozen water. The overwhelming majority of the planet's ice lies much farther south, in Antarctica, a continent so cold, so vast, and so remote that for much of history, humanity barely understood its scale. From space, it appears as a bright white disk surrounding the South Pole. But beneath that smooth surface lies the largest frozen structure on Earth. A structure that holds nearly 90% of all the ice on the planet. Understanding that continent would become one of the most important scientific challenges of the modern era. Because once researchers began mapping Antarctica in detail, they realized something that made the stability of its ice far more uncertain than anyone had once believed. And that discovery would change how scientists think about the future of the oceans. At first glance, Antarctica appears simple. From space, it looks like a smooth white continent, a frozen disk centered on the South Pole. But beneath that bright surface lies a landscape far more complicated than anyone once imagined. Under the ice, there are mountains. There are valleys. There are entire basins carved deep into the rock. And in many places, the ground beneath the Antarctic ice sheet lies below sea level. This discovery changed everything. For decades, scientists assumed the ice of Antarctica rested mostly on land above the ocean, much like a giant frozen plateau. If that had been true, the ice sheet might have remained relatively stable, even as the climate warmed. But radar surveys and satellite mapping revealed a very different reality. Large parts of the West Antarctic ice sheet sit on bedrock that lies hundreds of meters below sea level. The ice is not simply resting on land. It is anchored in basins that connect directly to the ocean. This means that warm ocean water can reach the edges of the ice from below. When that happens, the ice does not just melt from the surface, it melts from underneath. At the margins of Antarctica, enormous glaciers extend out over the ocean, forming floating shelves of ice that can stretch for hundreds of kilometers. These shelves act like giant barriers, holding back the massive glaciers flowing from the interior of the continent. As long as those floating shelves remain intact, they slow the movement of the ice behind them. But if the shelves thin or collapse, the glaciers feeding into them can begin to accelerate. And when glaciers accelerate, they carry vast amounts of ice into the sea. This process has already been observed in several regions of Antarctica. Satellite measurements show that parts of the West Antarctic ice sheet are losing mass each year as glaciers flow faster toward the ocean. Among these glaciers, one has become particularly famous: the Thwaites Glacier. Sometimes referred to by scientists and journalists as the Doomsday Glacier, Thwaites is one of the largest glaciers on Earth. It is roughly the size of Florida and plays a crucial role in stabilizing a large portion of the West Antarctic ice sheet. If Thwaites were to collapse completely, it could destabilize neighboring glaciers and trigger a chain reaction across the region. The result would not be an instant global flood, but it would begin a process that could eventually raise sea levels by several meters. And Antarctica contains far more ice than just the vulnerable glaciers of the West. The East Antarctic ice sheet, the largest body of ice on the planet, holds the majority of Antarctica's frozen water. In many places, this ice has remained stable for millions of years, protected by the extreme cold of the Antarctic interior. Together, the ice sheets of East and West Antarctica store an extraordinary amount of water, enough to raise global sea levels by around 58 meters if they melted completely. Add Greenland's contribution of roughly 7 meters, along with smaller amounts from glaciers around the world, and the total approaches a staggering figure: about 65 meters of potential sea level rise. 200 feet. Numbers like these are difficult to imagine in practical terms, but they translate into something very concrete. They mean that nearly every coastline on Earth would move inland. Entire cities would disappear beneath the ocean. River deltas, which support hundreds of millions of people, would be submerged. Island nations would vanish. Ports, highways, airports, and coastal power plants would be lost beneath rising seas. The modern map of the world, the one printed in atlases and displayed on navigation screens, would no longer match reality. But another important detail soon became clear to scientists studying these ice sheets. Not all ice affects sea level in the same way. Some of it is already floating, and that difference matters. Because while melting floating ice can transform ecosystems and ocean circulation, it does not directly raise the height of the sea. Only ice that rests on land has the power to do that. Understanding that distinction would become critical in predicting how the oceans might change in the future. And it leads to an important question. If different types of ice contribute differently to sea level, what happens when the planet begins warming? Which ice melts first? And which parts of the frozen Earth hold the greatest power to reshape the oceans? Once scientists understood where Earth's ice was stored, the next mystery became even more important. What actually controls the growth and disappearance of ice? Why does the planet sometimes accumulate enormous glaciers covering entire continents with frozen water, and at other times lose most of its ice entirely? At first glance, the answer seems simple. Temperature. If the planet becomes colder, ice forms. If the planet becomes warmer, ice melts. But the reality is far more complicated than that, because the history preserved in ice cores revealed something surprising. Ice ages do not begin simply because the Earth suddenly becomes cold. Instead, they begin when a delicate balance between sunlight, oceans, atmosphere, and geography shifts in just the right way. And one of the most important pieces of that balance lies far beyond the surface of the planet. It lies in space. The Earth does not orbit the Sun in a perfectly stable way. Over tens of thousands of years, the planet's orbit slowly changes shape. Sometimes it becomes slightly more circular. Sometimes it becomes slightly more elliptical. At the same time, the tilt of Earth's axis, the angle that creates our seasons, also changes gradually. And the direction the axis points slowly wobbles like a spinning top. These changes are extremely small, but over long periods of time, they alter how sunlight is distributed across the planet. Scientists call these patterns Milankovitch cycles, named after the Serbian mathematician Milutin Milankovic, who first calculated how orbital changes could influence long-term climate. The cycles unfold across three main rhythms. One lasts roughly 100,000 years, controlling how elliptical the Earth's orbit becomes. Another lasts about 41,000 years, affecting the tilt of the planet's axis. And a third cycle, about 23,000 years long, alters the timing of the seasons relative to Earth's orbit around the Sun. Individually, these changes are subtle, but together they influence how much solar energy reaches different parts of the planet, especially the northern continents where large ice sheets tend to form. When summers become slightly cooler in the northern hemisphere, snow that falls during winter may not melt completely during the following summer. Small patches of snow survive. The following winter adds more. Over centuries, those patches grow into glaciers. And once glaciers begin forming, another powerful feedback begins. Ice reflects sunlight extremely well. Fresh snow can reflect more than 80% of the sunlight that reaches it. Dark land and ocean absorb far more heat. So as glaciers expand, they reflect increasing amounts of solar energy back into space. That reflection cools the surrounding atmosphere, which allows more ice to form. The system begins reinforcing itself. Over thousands of years, these small changes can grow into enormous transformations. Ice sheets expand across continents. Sea levels fall as water becomes locked away on land. Entire ecosystems shift as the climate cools. This is how the great ice ages of the past began. Not as sudden catastrophes, but as slow planetary adjustments, a long chain of small changes that eventually reshaped the entire climate system. But the orbital cycles alone cannot explain everything, because the Earth's orbit has been shifting for millions of years. Yet, massive ice sheets have not existed throughout all of that time. For most of Earth's history, even when the orbital cycles favored cooler conditions, the planet remained too warm for large ice sheets to form. Something else had to change first, something involving the geography of the planet itself. Continents had to move, ocean currents had to shift, and only when those conditions aligned could the orbital cycles begin building the massive glaciers that would eventually dominate the poles. In other words, ice ages do not begin simply because the Earth becomes cold. They begin because the planet's entire system allows ice to survive. And once that happens, ice becomes one of the most powerful forces shaping the climate of the entire world. But this explanation reveals another important piece of the puzzle, because the same forces that allow ice to grow can also allow it to disappear. If the balance shifts in the opposite direction, if warming becomes strong enough, the feedback loops that once built the ice sheets can begin working in reverse. And when that happens, the frozen reservoirs of the planet slowly begin to unlock. But the real question is not simply whether the ice can melt. The history of Earth shows that it can. The real question is how large the consequences would be if it did. Because when scientists began calculating what 65 meters of sea level rise would actually mean for the modern world, they discovered something that would fundamentally change how we think about the map of civilization. If the growth of ice sheets is controlled by delicate balances between sunlight, atmosphere, and oceans, then their disappearance follows the same logic. But the process does not unfold as a simple mirror image. Ice does not melt in the same calm, gradual way that it forms. Once warming begins, a series of feedback loops can accelerate the process in unexpected ways. The first of these feedbacks begins with something deceptively simple: color. Fresh snow and ice are bright. They reflect a large portion of the sunlight that reaches them back into space. This reflective property, known as albedo, helps keep polar regions cold. But when ice begins to melt, darker surfaces appear: bare rock, soil, ocean water. These darker surfaces absorb far more sunlight than ice does. Instead of reflecting energy away, they trap heat, That additional heat warms the surrounding environment, causing even more ice to melt, which exposes even more dark surfaces. The feedback strengthens itself. This is why melting often accelerates once it begins. A second feedback loop exists beneath the frozen ground of the far north. Across large parts of the Arctic, vast regions of soil remain frozen year-round. This frozen ground, known as permafrost, contains enormous quantities of organic material that accumulated over thousands of years. When permafrost remains frozen, that material stays locked safely in the soil. But when temperatures rise, the frozen ground begins to thaw. And as it thaws, microbes begin breaking down the organic material trapped inside it. That process releases gases into the atmosphere, particularly carbon dioxide and methane. Both are powerful greenhouse gases. Their release traps additional heat in the atmosphere, which causes further warming, which thaws even more permafrost. Again, the system reinforces itself. These feedbacks illustrate why climate systems are rarely simple. Small changes can trigger chains of reactions that grow larger over time. But ice sheets introduce yet another powerful mechanism. When large glaciers flow toward the ocean, they often form floating shelves of ice at their edges. These shelves act as barriers that slow the movement of the ice behind them. But when warmer ocean water begins melting the shelves from below, the barriers weaken. Glaciers behind them accelerate. And as they accelerate, more ice flows into the sea. This process has already been observed in several parts of Antarctica and Greenland. Satellite measurements show glaciers speeding up after ice shelves thin or collapse. The loss of floating ice does not raise sea levels directly, but it allows land-based ice to move toward the ocean more quickly, and that ice does raise sea levels when it melts. The important point is that these processes are not isolated. They interact. Warming reduces ice cover. Reduced ice cover increases heat absorption. Additional heat melts more ice. Melting ice alters ocean circulation and atmospheric patterns. Each step feeds into the next. The result is a system that can shift gradually for long periods and then suddenly accelerate. Scientists sometimes describe these thresholds as tipping points. A tipping point is a moment when a slow change crosses a boundary, allowing the system to begin moving rapidly in a new direction. Ice sheets contain several potential tipping points. If certain glaciers retreat far enough inland, they may become unstable and continue collapsing even if temperatures stop rising. If large sections of ice shelves disappear, glaciers behind them may accelerate permanently. Once these processes begin, they can unfold over centuries or millennia. Not overnight, but once they start, stopping them can become extremely difficult. This is why understanding the mechanics of ice sheets matters so much, because the frozen water stored at the poles is not just a static feature of the landscape. It is a dynamic system capable of reshaping the oceans. And if that system were pushed far enough out of balance, the consequences would extend far beyond the polar regions. The coastlines of every continent would change. The places where humans built ports, cities, and trade networks would begin to disappear beneath rising seas. But to understand the full scale of that transformation, scientists had to do something even more dramatic. They had to imagine the world after the ice was gone. Not partially melted, not slightly reduced, but completely gone. And when they mapped that scenario for the first time, the result looked less like the world we know and more like an entirely different planet. When scientists first began modeling what the Earth would look like without its great ice sheets, the results were difficult to imagine. Numbers alone were not enough. 65 meters of sea level rise sounds enormous, but numbers rarely capture what that really means. Most people have experienced floods during storms or hurricanes. Water rises a meter or two, streets fill with seawater, and entire neighborhoods can be devastated. But 65 meters is not a storm surge. It is not temporary. It is a permanent transformation of the planet. To understand the scale of that transformation, researchers began mapping what would happen if all the ice currently stored on land returned to the oceans. The first thing they noticed was how quickly coastlines retreat. Many of the world's largest cities are built on coastal plains, broad stretches of land that lie only slightly above sea level. These areas are ideal for trade, transportation, and agriculture. Rivers reach the ocean there. Harbors form naturally. For thousands of years, civilizations have been drawn to these places. But the same geography that makes them attractive also makes them fragile. Flat land floods easily, and when the sea begins to rise, it spreads inland much faster than most people expect. One of the clearest examples appears in the United States, Florida. Seen on a modern map, Florida stretches like a long peninsula between the Atlantic Ocean and the Gulf of Mexico. Millions of people live along its coasts, drawn by warm climates and beaches that seem endless. But Florida is not a mountainous land. Much of the state sits only a few meters above sea level. Even its highest natural point rises just a little over 100 meters. The majority of its cities, Miami, Tampa, Jacksonville, Fort Lauderdale, exist on extremely low ground. In a world where the oceans rise 65 meters, Florida does not simply flood. It disappears. The southern half of the peninsula vanishes almost entirely beneath the ocean. Miami becomes part of the Atlantic. Tampa Bay expands far inland. Cities that once stretched along the coastline dissolve beneath shallow tropical seas. What remains are only scattered islands of higher ground. And Florida is just the beginning. Moving north along the eastern seaboard, the coastline begins retreating inland. River valleys that once carried fresh water toward the ocean become wide estuaries where salt water pushes deep into the continent. The Chesapeake Bay expands dramatically. Lowland regions across Maryland and Virginia begin to flood. The outer edges of the Carolinas break apart into chains of islands. Barrier islands vanish. Coastal plains transform into shallow seas. Then comes New York. New York City sits at the mouth of the Hudson River, one of the great natural harbors of North America. The city grew precisely because of that geography. Trade routes converged there, ports developed, financial power concentrated in a landscape shaped by rivers and tides. But that same geography leaves the city vulnerable. With 65 meters of sea level rise, large parts of lower Manhattan fall beneath the ocean. Wall Street, once the center of global finance, becomes part of a flooded harbor. The streets disappear beneath water. Subway tunnels fill permanently with seawater. The skyscrapers would remain standing for some time, but they would rise from a flooded city. The skyline would become a strange collection of towers emerging from a new inland sea. Further south, the transformation continues. Along the Gulf Coast, Louisiana is among the most vulnerable regions in North America. Much of the land already lies barely above sea level. With a dramatic rise in ocean height, the coastline shifts far inland. New Orleans disappears beneath the Gulf of Mexico. Large sections of southern Texas and Mississippi flood. Coastal wetlands expand into shallow seas. The Gulf itself spreads northward, reshaping the southern edge of the continent. Even Washington, D.C. is not immune. The Potomac River widens into a tidal bay. Low-lying districts flood permanently. The monuments and government buildings that define the capital sit dangerously close to the new shoreline. The geography of the eastern United States becomes almost unrecognizable. And yet, despite how dramatic these changes appear, North America is not the place where the impact of rising seas would be greatest. Because across the Atlantic and across the Pacific lie regions where hundreds of millions of people live on land barely higher than the ocean itself. Great river deltas, island nations, low coastal plains that support some of the most densely populated regions on Earth. And when scientists mapped those regions in a world with 65 meters of sea level rise, they discovered something even more shocking. Some countries would not simply shrink, they would nearly vanish from the map entirely. When scientists extended their maps beyond North America, the scale of the transformation became even clearer, because many of the most densely populated places on Earth sit on extremely low land. River deltas, floodplains, coastal plains built from thousands of years of sediment carried down by rivers. These landscapes are fertile, flat, and ideal for agriculture and trade. For thousands of years, they have attracted human settlements. Cities grew where rivers met the sea. Ports developed where ships could travel inland. Entire civilizations flourished in these coastal regions. But the same geography that made them prosperous also makes them vulnerable. When the ocean rises, deltas disappear. One of the most dramatic examples lies in South Asia, Bangladesh. This country sits on one of the largest river deltas in the world, where the Ganges and Brahmaputra rivers spread across a vast plain before reaching the Bay of Bengal. The land is fertile, heavily populated, and in many places only a few meters above sea level. Today, more than 170 million people live there. In a world where sea levels rise by 65 meters, much of Bangladesh would vanish beneath the ocean. Rivers would widen into shallow seas. Cities would disappear. Agricultural land would become tidal water. For millions of people, there would simply be nowhere left to live. Across the world in Europe, a similar vulnerability appears in the Netherlands. For centuries, the Dutch have fought against the sea, building dikes, pumps, and barriers to protect their land. Even today, about a quarter of the country lies below modern sea level. Without constant engineering, large parts of the Netherlands would already be underwater. But 65 meters of sea level rise is beyond anything those defenses were designed to resist. The North Sea would spread inland, swallowing much of the lowland landscape. Cities such as Rotterdam and Amsterdam would vanish beneath the water. The careful balance between land and sea that the Dutch have maintained for hundreds of years would be overwhelmed. The same pattern appears across Asia. Shanghai sits near the mouth of the Yangtze River, one of the most economically important regions in the world. Mumbai stands along the western coast of India, built on land reclaimed from the sea. Bangkok spreads across a low delta in Thailand. Tokyo stretches across coastal plains in Japan. These cities were built where trade routes met the ocean, but that location ties their fate to the height of the sea. In a world where the oceans rise 65 meters, many of these cities would disappear beneath the water. Rivers would become estuaries stretching deep inland. Coastal plains would transform into shallow seas. Even countries that appear geographically stable today would change dramatically. Large sections of northern Germany would flood. Denmark would fragment into islands. Low coastal regions of China would disappear. Parts of Southeast Asia would break apart into archipelagos where once there had been continuous land. The map of the world would no longer resemble the one humanity has used for centuries. Entire coastlines would shift. New seas would appear where farmland once existed, and regions that were once far inland would suddenly find themselves standing at the edge of the ocean. Cities like Denver, far from the modern coast, would become some of the closest large settlements to the new shoreline in North America. The transformation would not simply affect geography. It would reshape human civilization. Today, roughly 40% of the global population lives within 100 kilometers of the ocean. Ports, trade routes, and major cities are heavily concentrated along coastlines. If those coastlines move inland, the populations built around them must move as well. Scientists estimate that a world with drastically higher sea levels could force the relocation of billions of people over time, the largest migration in human history. Entire nations would face the challenge of moving their populations inland, Infrastructure would need to be rebuilt far from current coastlines. Economic centers would shift to new regions. Civilization would have to redraw its own map. Yet, despite how dramatic this transformation sounds, the Earth itself would not consider it unusual. Because long before humans built cities, the planet had already experienced worlds where the oceans were higher and the poles were warm. There was a time when Antarctica held forests instead of ice, a time when the Arctic Ocean was warm enough to support ecosystems that seem impossible today. In other words, a world without ice has already existed. And when scientists began studying those ancient climates, they discovered something surprising. Life on Earth did not collapse. It changed. But that ancient world was also very different from the one we inhabit today, because the warming that created it unfolded slowly across thousands of years. And that difference may be the most important part of the entire story. The idea of a world without ice may sound like a distant future scenario, but in the deep history of the planet, something very similar has already happened. Around 55 million years ago, the Earth entered one of the most dramatic climate events scientists have ever discovered. Geologists call it the Paleocene-Eocene thermal maximum, or simply the PETM. At the beginning of this period, the planet began warming rapidly. Global temperatures climbed by roughly 5 to 8 degrees Celsius, a massive shift on a planetary scale. The warming affected oceans, continents, and ecosystems across the entire world. But what makes the PETM remarkable is not just the temperature, it is the speed of the change. In geological terms, the warming happened very quickly. Carbon dioxide levels in the atmosphere rose sharply. Methane and other greenhouse gases increased. Ocean chemistry changed. Entire ecosystems were forced to adapt to a rapidly warming world. And yet, the Earth during this time looked very different from the frozen planet we know today. The Arctic Ocean, which today is covered by drifting sea ice for much of the year, was warm. Some studies suggest that surface waters in the Arctic may have reached temperatures around 20 degrees Celsius, warm enough for organisms that normally live in temperate or even subtropical environments. Instead of floating ice, the region supported forests, wetlands, and a wide range of animal life. Fossils discovered in Arctic sediments reveal an ecosystem that would seem impossible today. Ancient crocodile relatives swam through warm waters. Turtles lived in lakes and rivers. Dense vegetation covered landscapes that now lie locked beneath snow and permafrost. Even Antarctica was radically different. Today, the continent is buried beneath kilometers of ice. Temperatures plunge far below freezing, and almost no vegetation survives on land. But during the PETM, Antarctica supported forests. Fossilized pollen, leaves, and tree remains reveal that large parts of the continent were once covered with vegetation. Rivers flowed through valleys where glaciers now grind slowly toward the sea. If you could have stood in Antarctica during that ancient warm period, you would not have seen an endless white desert. You might have seen forests stretching across the landscape. The entire planet was warmer. Sea levels were higher, and ecosystems existed in places that now seem far too cold to support them. From the perspective of Earth's long history, this warm world was not unusual. The planet had experienced similar greenhouse climates before. But there was something important about the PETM that scientists continue to study carefully today. It offers a glimpse of how the Earth system behaves when large amounts of greenhouse gases enter the atmosphere. During the PETM, enormous quantities of carbon were released into the air and oceans. Scientists are still debating exactly where that carbon came from. Some believe it may have been released from methane deposits buried beneath the ocean floor. Others suggest volcanic activity may have played a role. Whatever the source, the effect was dramatic. The additional greenhouse gases trapped more heat in the atmosphere. Temperatures rose across the planet, and the climate system began adjusting to a new balance. But the adjustment was not easy. The warming triggered widespread ecological changes. Some marine species disappeared from the fossil record entirely. Ocean chemistry shifted as warmer waters absorbed carbon dioxide from the atmosphere. In many parts of the ocean, oxygen levels dropped, creating stressful conditions for marine life. On land, ecosystems reorganized. Plants migrated toward higher latitudes. Animal populations moved to follow the climates they were adapted to. Entire habitats shifted across continents as the planet warmed. Yet despite all these changes, life on Earth survived. The biosphere adapted. New ecosystems formed in the warmer world. Over time, the climate slowly stabilized again as natural processes gradually removed carbon from the atmosphere. But there is one critical difference between that ancient warming event and the climate changes unfolding today. The PETM warming happened over thousands of years. The changes we are experiencing today are unfolding far more quickly, and that difference may determine how well ecosystems and human civilization can adapt to what comes next. Because while the Earth itself has experienced warmer worlds before, our modern civilization has never existed in one. The ancient warming during the PETM offers an important lesson. The Earth can survive a warmer climate, but survival on a planetary scale does not mean stability for the systems living on it. During the PETM, ecosystems shifted across continents and oceans as temperatures rose. Some species adapted, others disappeared. New ecological communities formed as plants and animals migrated into newly suitable environments. But those changes unfolded slowly. Thousands of years passed as the climate warmed and ecosystems gradually reorganized themselves. Forests expanded northward. Marine life adjusted to new ocean conditions. The biosphere had time to respond. That timescale matters. Evolution and migration require time. When environmental changes happen gradually, many species can adapt. Populations shift their ranges. Genetic variations that favor survival become more common. Over generations, life reorganizes itself to match the new climate. But when the rate of change accelerates, adaptation becomes much more difficult. And that is the situation scientists are studying today. Since the beginning of the industrial age, human activity has released enormous quantities of carbon dioxide into the atmosphere. Coal, oil, and natural gas, fuels formed from ancient plants and microorganisms buried over millions of years, are now being burned at extraordinary rates. The carbon stored in those fuels is returning to the atmosphere. As it accumulates, the atmosphere becomes more efficient at trapping heat from the sun. Global temperatures begin to rise. This process is often described as the greenhouse effect, but the concept is simpler than it sounds. Certain gases in the atmosphere absorb and re-emit heat, slowing the rate at which energy escapes back into space. More greenhouse gases mean more heat retained within the Earth system. And the numbers show a dramatic change. Before the industrial era, atmospheric carbon dioxide levels remained around 280 parts per million for thousands of years. Today, that number has climbed above 420 parts per million and continues rising. The increase is happening far faster than most natural climate shifts observed in the geological record. Even during the PETM, when large amounts of carbon entered the atmosphere, the process appears to have unfolded more slowly than the current rise. In other words, the Earth has experienced high greenhouse gas levels before, but rarely at this speed. And speed changes everything. Because rapid warming triggers the same feedback mechanisms that helped control ice sheets in the past, but now they may begin operating in reverse. One of the most important of these feedbacks involves ice itself. When ice melts, the bright reflective surface disappears. Darker ocean water and exposed land absorb more sunlight, increasing local temperatures. That additional heat melts more ice, expanding the process. Scientists have observed this effect clearly in the Arctic. Over recent decades, the extent of summer sea ice has declined significantly. Large areas of dark ocean now absorb sunlight that once would have been reflected back into space by ice. This change amplifies warming in the polar regions. But the Arctic is not the only concern. Another potential feedback lies beneath the frozen soils of the far north. Permafrost, ground that has remained frozen for thousands of years, contains vast stores of organic carbon. When this ground thaws, microorganisms begin breaking down that material, releasing carbon dioxide and methane into the atmosphere. Methane is an especially powerful greenhouse gas. Even relatively small releases can contribute to additional warming. This creates a feedback loop. Warming thaws permafrost. Thawing releases greenhouse gases. Those gases trap more heat, which leads to further warming. Scientists continue to study how strong this effect may become over time. But permafrost is only one of several potential tipping points within the Earth system. Ice sheets themselves may contain thresholds where gradual change suddenly accelerates. Certain glaciers in Antarctica and Greenland rest on bedrock that slopes downward beneath the ice. If warming causes those glaciers to retreat far enough inland, ocean water can begin flowing beneath them more easily. Once that happens, the glaciers may become unstable. The retreat continues even if temperatures stop rising. In other words, some parts of the ice sheet could pass a point where their long-term collapse becomes difficult to stop. This does not mean the world would suddenly flood overnight. Ice sheets respond over centuries and millennia. But once these processes begin, they may continue unfolding long after the initial warming that triggered them. That possibility is why scientists study the polar regions so intensely today. Because the frozen reservoirs of Antarctica and Greenland are not just relics of the past, they are active parts of the climate system. And if they begin losing mass rapidly, the consequences would eventually reach far beyond the poles. Coastlines would move. Cities would face rising seas, and the map of human civilization would slowly begin to change. But the question is not simply whether warming is happening. The deeper question is how the planet responds once certain thresholds are crossed. Because in Earth's long history, climate shifts have sometimes triggered transformations far larger than anyone expected. And understanding those transformations requires looking not only at the present, but at the strange clues left behind by ancient worlds. By the time scientists began studying the modern ice sheets in detail, one thing had become clear. The frozen poles are not static. They move. Glaciers flow like extremely slow rivers, sliding toward the ocean under their own immense weight. Ice shelves fracture and drift across polar seas. Entire sections of ice sheets can thicken, thin, advance, or retreat, depending on the balance between snowfall and melting. From space, these changes are subtle, but satellites have now watched them for decades, and what those satellites have seen is beginning to reveal a new layer of the story. Across parts of Antarctica and Greenland, the ice is changing faster than scientists once expected. Some glaciers are thinning, others are accelerating, and in certain regions, enormous cracks are spreading across ice shelves that once seemed stable. One of the most closely studied areas lies along the coast of West Antarctica. Here, a vast network of glaciers flows from the interior of the continent toward the Amundsen Sea. Among them is one of the most famous glaciers on Earth, Thwaites Glacier. At first glance, Thwaites looks like many other Antarctic glaciers, a massive river of ice slowly pushing toward the ocean. But the scale of this glacier is difficult to comprehend. It covers an area roughly the size of Florida, and it acts as a critical stabilizing structure for a large portion of the West Antarctic ice sheet. If Thwaites remains stable, the glaciers behind it move slowly. But if it weakens or retreats, the entire region could begin draining ice toward the sea much faster. For this reason, researchers have spent years studying the glacier using satellites, aircraft, radar, and underwater robots designed to explore the ocean beneath the ice. What they have discovered is both fascinating and unsettling. Warm ocean currents are reaching the base of the glacier. Deep beneath the floating ice shelf, relatively warm seawater circulates through cavities and channels carved into the underside of the ice. As that water moves, it melts the glacier from below. This process is invisible from the surface, but it is reshaping the structure of the ice. The floating shelf that once helped stabilize the glacier is thinning. Cracks are spreading across its surface. Some sections have already broken away into enormous icebergs that drift slowly into the Southern Ocean. Each time a piece breaks off, the glacier behind it loses part of the barrier that once slowed its movement. The ice begins to flow faster, and as it flows faster, more ice enters the ocean. Scientists sometimes refer to Thwaites as the Doomsday Glacier. The name does not mean the world will end if it collapses, but it reflects how important this glacier is to the stability of the surrounding ice sheet. If Thwaites were to retreat far enough inland, it could destabilize neighboring glaciers that currently rest behind it. Those glaciers hold enough ice to raise global sea levels by several meters. And once such a retreat begins, it may continue even without additional warming. This possibility illustrates one of the most complex aspects of ice sheet behavior. Some changes are reversible, others are not. In certain cases, glaciers may reach a point where retreat becomes self-sustaining. The geometry of the bedrock beneath the ice allows ocean water to penetrate farther inland, melting the glacier faster as it retreats. Scientists call this process marine ice sheet instability. It is one of the reasons why predicting the future behavior of Antarctica remains so difficult. But the mystery does not end there. Because while parts of West Antarctica appear vulnerable, other regions of the continent have remained remarkably stable. The East Antarctic ice sheet, which holds the majority of Antarctica's ice, has endured for millions of years. Temperatures in the interior remain so cold that surface melting is extremely rare. In many areas, snowfall continues accumulating year after year, slowly adding new layers to the frozen plateau. This creates a puzzle. If the planet warms, will the East Antarctic ice sheet remain stable, or could certain thresholds eventually push even this enormous ice mass into retreat? Scientists do not yet know the answer, and that uncertainty is part of what makes Antarctica one of the most closely studied regions on Earth. Because the continent holds enough ice to transform the oceans, but the pace and pattern of that transformation remain uncertain. Some glaciers may respond quickly, others may remain stable for centuries. And somewhere within this enormous frozen system lie the tipping points that could determine the future of Earth's coastlines. But to understand what those tipping points might mean, scientists had to step back and examine the entire planet. They needed to look not only at individual glaciers, but at the global climate system that connects oceans, atmosphere, and ice. And when they did, they discovered something even more surprising. Because the future of the ice sheets may depend on forces far beyond the polar regions themselves. As scientists studied the ice sheets more closely, they began to realize something important. The future of the ice does not depend only on the temperature of the air above it. It also depends on the oceans. Because the oceans move enormous amounts of heat around the planet. Warm currents carry energy from the tropics toward the poles, while cold currents return dense water back toward the equator. These flows form a vast global circulation system connecting every ocean basin. Changes in that circulation can alter how much heat reaches the polar regions, and even small changes can have powerful consequences for ice. One of the most important of these systems lies in the Atlantic Ocean. Oceanographers call it the Atlantic Meridional Overturning Circulation, or AMOC. It acts like a gigantic conveyor belt. Warm surface water flows northward through the Atlantic, releasing heat into the atmosphere as it travels toward Europe and the Arctic. As the water cools, it becomes denser and sinks, eventually flowing back southward through the deep ocean. This circulation helps regulate the climate of large parts of the northern hemisphere. But scientists have noticed signs that the system may be changing. As Greenland's ice sheet melts, large volumes of fresh water enter the North Atlantic. Fresh water is less dense than salty ocean water, which can interfere with the sinking process that drives the deep return flow of the circulation. If enough fresh water enters the system, the circulation could weaken, and if it weakens, heat transport through the Atlantic could change dramatically. Some regions might cool, others might warm. Climate systems are rarely simple, but the key point is this: the oceans and the ice sheets are deeply connected. Changes in one can influence the other. In the Southern Ocean surrounding Antarctica, similar processes are unfolding. Warm water from deeper layers of the ocean can sometimes rise toward the surface and flow beneath floating ice shelves. These waters may be only a few degrees above freezing, but that is enough to melt ice when it reaches the underside of a glacier. Unlike surface melting, this process happens out of sight. The ocean slowly erodes the ice from below. Over time, the shelves thin, cracks widen, and the glaciers they once held back begin to accelerate toward the sea. This interaction between ocean heat and polar ice is one of the reasons scientists rely heavily on satellites and underwater instruments to monitor Antarctica today. Without those tools, many of these changes would remain invisible. But the deeper researchers examine the polar system, the more they see how interconnected the planet truly is. Atmospheric circulation influences ocean currents. Ocean currents influence the stability of ice shelves. Ice sheets influence sea levels and the reflection of sunlight. Each part of the system feeds back into the others, and when that system shifts, the consequences spread across the entire planet. Yet, despite decades of research, many aspects of these processes remain uncertain. Climate models can simulate possible futures, but the real Earth often behaves in ways that are more complex than any model can perfectly predict. Some glaciers may retreat gradually. Others may remain stable for long periods before suddenly accelerating. The timing of these shifts remains one of the great unanswered questions of modern climate science. But one thing is clear: the frozen reservoirs of Greenland and Antarctica hold enough water to reshape the map of civilization, and even small fractions of that ice can have enormous consequences. A rise of 1 meter in global sea level would already threaten many coastal cities. 3 meters would redraw large portions of coastlines. 10 meters would transform entire regions of the world. 65 meters would create a completely new geography. Yet the Earth itself has experienced high seas before. Long before humans built cities or nations, oceans covered areas that are now dry land. Coastlines moved. Ecosystems migrated. Life adapted to a different world. Which raises an uncomfortable question. If rising seas are not new in the long history of Earth, what does that history tell us about the future? Because there was a time not so long ago in geological terms when humans themselves faced rising oceans, and the story of how they survived that transformation may offer clues about what lies ahead. About 8,000 years ago, the people of Northern Europe were living in a land that no longer exists. Today, the North Sea separates the island of Britain from mainland Europe. Cold, gray waters stretch across the horizon, and ships cross the sea between ports in England, the Netherlands, and Scandinavia. But thousands of years ago, much of that sea was dry land. A vast, low plain connected Britain to the European continent. Rivers wound across open grasslands. Forests grew in sheltered valleys. Herds of animals moved across landscapes where hunters followed seasonal migrations. Archaeologists now call this lost land Doggerland. For the people who lived there, it was simply home. Stone tools, animal bones, and fragments of ancient campsites have been recovered from the seabed by fishing trawlers and underwater surveys. These discoveries reveal that the region was once a thriving environment, rich in wildlife and fresh water. But the world of Doggerland existed at the end of the last ice age. At that time, enormous ice sheets still covered parts of North America and northern Europe. Much of the planet's water remained locked inside those glaciers. Because so much water was frozen on land, global sea levels were lower than they are today. The coastlines of Europe extended far outward. What is now the North Sea was once a broad landscape of plains, rivers, marshes, and forests. For thousands of years, humans lived there. They hunted deer and wild cattle. They fished in rivers and coastal lagoons. They gathered plants and built small communities across the lowlands. The land was fertile, and the climate was slowly warming as the last great ice sheets of the Ice Age began to melt. But as those glaciers retreated, the oceans began rising. At first, the changes were subtle. A shoreline moved a little farther inland. A river valley slowly widened as seawater pushed upstream. Wetlands expanded where dry ground once existed. For the people living in Doggerland, these changes would have unfolded across generations. The sea crept closer over centuries, not days. Each generation would have seen familiar landscapes slowly transforming. A hunting ground becomes a marsh. A forest becomes a tidal inlet. A valley becomes an arm of the sea. Communities would have adapted as best they could. They moved their camps to higher ground. They followed the shifting coastline inland. Fishing may have become more important as marine waters expanded across the plains. For thousands of years, humans adjusted to the rising sea. But the process did not continue forever. Around 6,200 BCE, a dramatic event struck the region. Off the coast of Norway, a massive underwater landslide occurred along the continental shelf. Millions of tons of sediment suddenly collapsed down the slope of the seafloor, displacing enormous volumes of water. The result was a giant wave. Today, scientists call this event the Storegga tsunami. The tsunami surged across the North Atlantic and into the shallow seas covering Doggerland. Coastal regions were flooded almost instantly. Waves raced across low-lying landscapes where human communities had lived for generations. For the people still remaining on the shrinking plains, the event must have been catastrophic. The wave did not create the rising sea. That process had already been underway for centuries. But the tsunami may have been the final blow. After the event, much of the remaining land was submerged. Over time, the sea covered the entire region. Doggerland disappeared beneath the North Sea. Today, the only traces of that lost landscape lie beneath the water, preserved in sediments and scattered artifacts recovered by fishermen and marine archaeologists. It is one of the clearest examples of how rising seas can transform the geography of the world. But the story of Doggerland also reveals something else. The people who lived there did not vanish. They moved. As the ocean advanced, communities gradually migrated toward higher ground. Some likely moved west toward the hills of Britain, others traveled east into mainland Europe. Human societies adapted. The coastline changed, but life continued. Yet the rising seas of the Ice Age unfolded over thousands of years. The people of Doggerland had generations to respond. The question scientists ask today is whether modern civilization would have the same amount of time. Because the cities we have built along the coasts are far larger than the villages of prehistoric hunters, and the infrastructure surrounding them is far more complex. Which means that if coastlines begin shifting again, the challenge of adaptation could be far greater than anything our ancestors faced. The story of Doggerland reminds us of something important. Rising seas are not a new phenomenon in the history of Earth. The coastlines of the planet have moved many times before. Ice ages lowered sea levels, exposing vast landscapes that are now underwater. Warmer periods returned that water to the oceans, drowning valleys and plains that once supported life. Humanity itself has already lived through one of these great transitions, but the scale of modern civilization changes the challenge dramatically. 8,000 years ago, the people living in Doggerland were small communities of hunters and gatherers. Their settlements were temporary. Their tools were simple. When the coastline shifted, they could pack their belongings and move. Today, the situation is very different. Modern cities contain millions of people. They rely on roads, bridges, power grids, ports, and vast systems of infrastructure. Entire economies depend on coastal trade routes and harbors that have developed over centuries. Moving a prehistoric village is one thing. Moving a modern megacity is another. Yet in some parts of the world, people are already confronting this challenge. One of the most famous examples is Venice. For centuries, the city has stood at the edge of the Adriatic Sea, built across a network of islands and canals. Venice has always lived with water. Tides flood the streets during certain seasons, and the city has developed ways to adapt to these periodic events. But in recent decades, flooding has become more frequent. To protect the city, Italy constructed an enormous system of movable barriers known as the Mose Project. When tides rise too high, massive gates can lift from the seafloor, temporarily blocking the incoming seawater. The project cost billions of dollars, and it illustrates the lengths modern societies may go to defend coastal cities. Another example lies in the Netherlands. For centuries, the Dutch have engineered their landscape to hold back the North Sea. Dikes, pumps, canals, and massive flood barriers protect land that in many cases lies below sea level. Without this infrastructure, large parts of the country would flood. The Netherlands has become one of the world's most sophisticated examples of how technology can reshape the relationship between land and water. Yet even the Dutch recognize that their system has limits. Their defenses are designed for the present coastline, not for a world where oceans rise tens of meters higher. In other places, governments are beginning to consider more drastic solutions. Indonesia, for example, faces severe flooding in its capital city. Jakarta, home to more than 10 million people, sits on low coastal land that is slowly sinking as groundwater is extracted from beneath the city. Combined with rising sea levels, the problem has become so severe that Indonesia has begun building a new capital city on the island of Borneo. The new city, called Nusantara, is intended to replace Jakarta as the political center of the country. It is one of the most dramatic examples of a nation planning for a future where coastal cities may become increasingly vulnerable. Around the world, similar discussions are beginning to emerge. Should cities build barriers? Should they elevate infrastructure? Or should they eventually retreat inland? These questions do not yet have simple answers, but they reveal something important about the future of coastal civilization. Adaptation is possible. Human societies are remarkably capable of engineering solutions, relocating populations, and reshaping landscapes. Yet the scale of those adaptations depends on how fast the oceans change. Slow changes allow societies to adjust over time. Rapid changes are far more disruptive. And that brings the story back to the frozen reservoirs of the poles. Because Antarctica and Greenland are not simply remote landscapes. They are the locks holding back the oceans. As long as their ice remains stable, the coastlines of the world remain roughly where they are today. But if that balance shifts dramatically, the map of civilization may begin changing again, just as it did thousands of years ago for the people of Doggerland. The difference is that today, billions of people live near the sea, and the cities they built have become some of the most important centers of human civilization. Which raises a final question. if the ice sheets truly hold the power to redraw the world's coastlines, what does that mean for the future of the planet itself? Because when we step back and look at Earth across billions of years, the answer reveals a much larger story. When we step back from coastlines, cities, and the daily concerns of human civilization, the story of Earth's ice begins to look very different. From the perspective of the planet itself, ice ages are temporary chapters. The Earth has existed for about 4.5 billion years. Over that immense span of time, the climate has shifted repeatedly between warmer and colder states. Continents have collided and broken apart. Oceans have opened and closed. Entire ecosystems have appeared, flourished, and vanished. Compared with those immense geological changes, the modern world is surprisingly recent. Human civilization, cities, agriculture, written history, has existed for only about 10,000 years. That period coincides almost perfectly with the most recent interglacial, a relatively warm and stable phase between major ice ages. During this time, glaciers retreated from large portions of the northern hemisphere. Sea levels stabilized, and the climate became remarkably consistent. It was within that window of stability that civilization emerged. Agriculture developed, permanent settlements formed, trade networks expanded. Eventually, cities rose along rivers and coastlines where the geography of the world remained predictable enough for complex societies to grow. But that stability is unusual. When scientists examine the climate record stretching back hundreds of thousands of years, they see a pattern dominated by long glacial periods interrupted by shorter warm intervals like the one we live in today. In other words, the stable climate that allowed civilization to flourish may be the exception rather than the rule. Ice ages come and go. Sea levels rise and fall. The geography of the world slowly changes as the climate system shifts between colder and warmer states. Yet the Earth itself continues. The planet does not depend on ice sheets to survive. During ancient greenhouse periods, the poles were warm and forests grew near regions that are now buried beneath ice. Sea levels were higher, ecosystems were different, but life still thrived across the planet. From a geological perspective, a world without ice is not a broken world. It is simply a different one. This realization leads to an uncomfortable truth. When scientists talk about melting ice sheets and rising seas, they are not describing the destruction of the Earth itself. The planet will continue orbiting the sun regardless of what happens to its ice. What may change is the environment that human civilization has grown accustomed to. Our cities, our trade routes, our agriculture, and our infrastructure were all built during a relatively narrow period of climatic stability. Coastlines remained mostly fixed. Seasons followed predictable patterns. Ocean circulation remained within familiar ranges. Civilization expanded across landscapes that seemed permanent. But those landscapes exist only because enormous quantities of water are currently locked away in ice. The frozen reservoirs of Greenland and Antarctica act like a giant storage system for the oceans. As long as that water remains frozen on land, sea levels stay relatively low. But if the ice were to melt, that balance would shift. Coastlines would move inland. Cities would face rising seas. Entire regions of the world would gradually transform. From the perspective of Earth's history, this would not be unprecedented. The planet has experienced such transformations many times before. But from the perspective of modern civilization, the change would be profound. Because the world we built assumes that the coastlines of today will remain where they are. And that assumption depends on something remarkably fragile: ice. Frozen water sitting quietly at the top and bottom of the planet. Water that has the power to redraw the map of the world if it ever returns to the sea. And that realization leads to one final question. Not about the past, not even about the distant geological future, but about the choices humanity makes in the present. In the end, the story of Earth's ice is not just a story about glaciers and oceans. It is a story about time. Planetary time moves slowly. Continents drift across the surface of the Earth at speeds measured in centimeters per year. Ice sheets grow and retreat over thousands of years. Ocean currents shift gradually as the climate system adjusts to new balances of heat and energy. Against that immense backdrop, human civilization is incredibly young. The cities we live in today are only centuries old. Many modern nations have existed for less than 200 years. Even the oldest surviving civilizations represent only a tiny fraction of the planet's history. And yet, those civilizations were built on an assumption that the climate surrounding them would remain relatively stable. That assumption shaped everything. Farmers planted crops based on predictable seasons. Ports were built where the sea met the land. Cities grew along coastlines and river deltas where trade and transportation were easiest. Over time, infrastructure spread across those landscapes. Roads, railways, bridges, power plants, and entire metropolitan regions that depend on the geography remaining largely unchanged. But the geography itself depends on something far older than civilization. It depends on ice. As long as the great ice sheets remain stable, the oceans remain close to their current level. Coastlines stay where they are. Harbors remain usable. Cities built near the sea continue functioning. But if that balance changes, the map of the world begins to shift. Not instantly, not in a single dramatic moment, but gradually, over generations, as water returns to the oceans and coastlines move inland. Human societies would adapt, just as people adapted in the distant past when the seas rose after the last ice age. Communities would relocate. Infrastructure would move inland. New cities would grow where the new coastlines eventually settle. Civilization would continue, but it would do so in a different landscape. And that brings the story back to the place where it began, New York Harbor. The Statue of Liberty still stands there today, looking out across the Atlantic just as she has for more than a century. Ferries cross the water. Cargo ships move through the harbor. The skyline rises behind her, a symbol of the modern world. All of it exists because the oceans remain where they are, because enormous quantities of water remain frozen at the poles, because Antarctica and Greenland still hold the seas back. But if we imagine that water slowly returning to the oceans, meter by meter, century by century, the familiar geography of the world begins to change. The harbor widens. The shoreline moves inland. Lower Manhattan disappears beneath the water. Eventually, even the pedestal of the statue vanishes beneath the rising sea. And at last, the torch that once welcomed ships into the harbor sinks beneath the waves. Not because the earth has ended, but because the planet has entered another chapter in its long history. The ice melts, the oceans rise, the map changes, and life, as it has always done, continues in a world that no longer looks the same. The earth does not care where our coastlines are drawn, but for the civilizations that live along those coastlines, the difference between frozen ice and open ocean may determine the shape of the world for generations to come. And that is the quiet power of ice, a force capable of redrawing the planet, one melting glacier at a time.